Okay, let's make a start. So last time we went through and we found from a dipole the E and the H fields at some point R and time t. Okay, and we started looking at the Poynting vector. Okay, so we know that P equals E cross H. Okay, we know that we've got the E field is in the A phi direction, A theta direction, and the H field's in the A phi direction, so they're orthogonal, and the cross product of that's going to give the Poynting vector being in the AR direction. Okay, so power flow is away from the source. Okay, and so the Poynting vector then is just going to be the magnitude of E times the magnitude of H in the AR direction. Okay, so we could write that down. So it's going to be P is going to be equal P squared omega to the fourth sine omega times T minus R on C. That's going to be squared, so there's two of them. And it's going to be sine squared theta divided by 16 pi squared epsilon naught C cubed R squared. Okay, and we can see that okay, first of all it's going off as 1 on R squared, which is what we'd expect. If you're emitting power from a particular place, it's a finite amount of power, then as you go further away it spreads out over a sphere, which a sphere has a radius or a surface area proportional to R squared. Okay, so that's what we expect, that the power is dropping off a factor of 1 on R squared. We can look at the time average of that. Okay, so we can see that it's Poynting vector, the power or Poynting vector goes as sine squared omega t. Okay, in it's a function of time, but that function is a sine squared term. Okay, so if you look at what sine squared of x looks like, okay, and this is x, then it's going to look something like this. Okay, it's going to be this, and that's that's pi, and this is 2 pi. Okay, and the maximum is going to be 1. Okay, so it's a positive function. It's always bigger than 1. Okay, because it's square. Okay, so we can find the average of that. It turns out to be a half. Okay, so the average of sine squared would be given by 1 on 2 pi times the integral from 0 to 2 pi sine squared x dx. Right, that's what it would be. Okay, and if you substitute sine squared x with 1 minus, I think it's a half outside of 1 minus cos 2x. Okay, and then you can do that integral and you'll find it comes out to 1/2. Okay, so probably you've had that before in other courses. Okay. Okay, so this is going to equal in the end. It's going to come out to be 1/2. Okay, the average value here. Okay, so then we can integrate that. We can find the average of P over time. Okay, and that's going to give us P equals P squared omega to the fourth sine squared theta. Okay, divided by 32 pi squared epsilon naught C cubed on R squared. Okay, so these are all in the AR direction. Okay, so that's P av. Okay, so at any position R, okay, then that would be the average Poynting vector. Okay, at that position. Now we can also look at integrating that over a sphere. Okay, so say if we're at the origin, okay, and we take a sphere of radius R. Okay, so the dipole's at the origin, a sphere of radius R. Okay, and then we've got P coming out in this AR direction from the surface of that sphere. Okay, and we've got little bits of ds. Okay, on that surface. Okay, and we want to integrate P dot ds over the whole sphere to find out the total amount of power that's being emitted into space by that dipole. Okay, so we can do that, but we need to remember that we're going to use spherical coordinates. Okay, and you know that in spherical coordinates, so this is z x, so it's y, and this is x. You define, you have an r instead of an xyz, you have an r, you have a theta, and you have a phi. Okay, so you define a point in space, and when you define an area or like a surface area on that sphere of distance r, okay, then this ds, the magnitude of it, is going to be product of these two small lengths, right? Okay, and remember that this length here, okay, is going to be r times d theta, okay, in that direction. Okay, because the thing with spherical and cylindrical is that the ds's and dv's depend on where you are. Okay, it's not like in Cartesians it's always dx dy, right? But here it's something different. Okay, and this length is r, I think it's d phi times sine of theta, right? Okay, of course once you get down to the equator of the sphere, then it's r d phi, but as you go up to the poles, then you're going around a smaller circle, right? So it's going to go to 0, right? So ds is the magnitude of ds is I think it's r squared sine theta d phi d theta or something like that, right? Okay, so we've got to do the integral like that. So the integral I think we do to get the P av total radiated, it's going to be I think we go from 0 to 2 pi for phi, okay, and 0 to pi for theta, and it's going to be P av r squared sine theta d theta d phi. Okay, so integrating, d phi is just going to be 2 pi, so that's going to be integral from 0 to pi p squared omega to the 4th on 16 pi epsilon naught c cubed, and the r's will cancel out. Okay, you've got an r squared here and an r squared there, and it'll be sine cube theta d theta. Okay, and so this is a constant, right? This is a constant. Okay, and this is the only thing we have to integrate, right? And just it turns out you can look up in tables. Sine cube theta happens to be equal to 4/3, right? Okay, if you do the integral, probably by splitting up the sine into various parts. Okay, and you'll eventually find that it's equal to 4/3. Okay, so that means that the total radiated power is going to be p squared omega to the 4th on 12 pi epsilon naught c cubed. Okay, so we're going through the time average. Okay, and just note sometimes this k has been brought in. K is what's called the wave number. Okay, it's 2 pi on the wavelength, which happens to be omega on c. Okay, so some of the formulas here have got k in them. Okay, so and we end up with this. Okay, p squared omega to the 4th. Okay, on 12 pi epsilon naught c to the cube. Okay, because that's k is omega on c. Okay, so it's total power radiated, and you can see it's independent of r, right, which is what you expect. Okay, so you're emitting a certain amount of power from the dipole at the origin. As you go further and further out, and you encompass, and the power's radiating away. Okay, and you have a sphere that encompasses that. You wouldn't expect that any power's getting added or taken away. It's just going out through space. Okay, so it doesn't matter which size radius of sphere you take, it's going to be the same amount of power exiting that sphere. Okay, because the only source is the dipole. Okay, so far we've just looked at, any questions on that? Okay, so far we've just looked at these 1 on R components. Okay, and we said that's what we're interested in. Okay, now we could find the pointing. So when we found the pointing vector just then, we only looked at the E and H that dropped off as a 1 on R, the far field or the radiated components of E and H. We could have done the pointing vector for all the components of E and H. Okay, so E will have some component. It has a component that goes as 1 on R plus some other ones that go as 1 on R squared or 1 on R cubed. And same with H. It has the 1 on R component plus those other components that aren't 1 on R and not 1 on R. Okay, with 1 on R squared or 1 on R cubed. Okay, and so the pointing vector will be the multiplication of these, the cross product of these two vectors. Okay, and the cross products has a distributive property, so we can just multiply out those two brackets, and get a number and add up a number of cross products. Okay, so it's going to be a cross product of E not 1 on R with H 1 on R, E 1 on R with H not 1 on R, E not 1 on R cross product with H not 1 on R plus what we had before. Okay, just the cross product of the E and H 1 on R factors. Okay, so and we can take the time average of that. Okay, we can take the time average of the whole thing, for all the parts in any case. Okay, so this sort of triangular brackets means time average. Okay, so we can do that. Okay, we divide it up into groups. So I think this is meant to be not 1 on R here. Okay, so there's a mistake in the slides. So we've got all the terms in the cross product that involve something with not 1 on R here, and what we had before. What we just calculated is this term here. Okay, it turns out we'll take time average. All of these add up to 0. Okay, and the only thing that transports energy away from the dipole through space, okay, is these 1 on R terms. Okay, the cross product of the 1 on R term of E and the cross with the 1 on R term of H. Okay, all of these the time average of the pointing vector is 0. Okay, it's like inductor or capacitor; they don't dissipate any energy. Energy's not going away from the dipole in any sense. So if that's providing, of course, you just have the dipole in free space. Okay, there's nothing else nearby to interact. Okay, if you had perhaps something very close to the dipole in the region of the near field, then perhaps you might get some energy transfer from the dipole to that other object via these near field terms. Okay, but if it's in free space and you're far away, then and you have a receiver, then the thing that's transferring this energy is these far field terms. Okay, so this is the one that we're interested in, and all these near field terms don't transport energy away from the dipole if there's just free space around it. Okay, so we can go through some examples. Say a mobile phone transmits with a power of 0.2 watts. What is the electric field at 1 meter distance, and what is that 1 kilometer distance? Okay, so we know that the average power emitted from the from the antenna, okay, which is we're assuming it's a dipole, and we're also assuming it's radiating out in a spherical pattern. Okay, so it's that radiation is equal in all directions, which isn't necessarily true, but it's an assumption here. Okay, then we know that the average power is going to be E cross H, the time average of E cross H dot ds. Okay, and so we know that E on H equals this neta, right? So the magnitude of this integral is just going to be E squared divided by neta. We have a time average, so it's going to be a half, because it involves a squared, a sine squared term. Okay, and we're taking time average to be a half, and then this surface area integrated over a sphere. Okay, so we're talking about a sphere here. That's just going to be 4 pi r squared, right? Because the surface area of a sphere is 4 pi r squared. Okay, so that's the power going out through, or at average power being emitted from the going out through the sphere after integrating over it. Okay, and that's going to be fixed. That's what's going to equal 0.2 watts. Okay, so we can say then that E at a position R is just going to be the square root of 2 times P neta divided by 4 pi r squared. Okay, so at 1 meter it gives 3.46 volts per meter, and at a kilometer it's 1,000 times less. Okay, so that's just using our results that we've had so far to, or our understanding to, apply it to some example situation. Okay, so we also looked at, we've looked at a dipole. Okay, we can also look at instead of having at the origin. So in the last example, we had this dipole which was orientated in the z direction and had these plus or minus charges oscillating. Okay, and it was separated by some small distance L. Okay, we could also look at having a small current element, so a small piece of wire of length L, orientated in the z direction. Okay, at the origin. Okay, and we could say, well, maybe there's a current, sinusoidal current flowing in that small piece of wire. Okay, and we know that from the charge continuity equations. Okay, that we can't create or destroy charges, right? And current is moving charges, so those charges have to go somewhere. So we could say, well, those charges end up filling up some Q, plus or minus Q at the ends of that short piece of wire. Okay. So and we had the charge continuity equation that we looked at before, where we had we said that the rate of time, the time rate of change of charge entering volume or something has to equal the current coming in or going out. Okay, that's J. We had some time ago. Okay, so we know that at one of these edges or one of these ends, the dq dt, it has to be equal to the current going in. Okay, and we're going to say that the current on that piece of short piece of wire is cos some magnitude I naught times cos omega t. Right. Okay, so dq dt, what the charge that ends up here. So the current's taking charge from here, positive charge from the bottom, placing it up the top. Okay, and depending on the sign of cos, of course. So and then as the sign of cos changes to negative, it takes positive charge on the top and puts it on the bottom. Okay, so dq dt at one of these, at this point here, is going to be I cos omega t. Right. So we can integrate that, and we can find q as a function of time. Okay, so q is going to be omega naught sine omega t divided by omega. Right. Okay. And remember, when we defined what a dipole was, we defined a dipole as charges, a charge q separated by some small distance L. Okay. So the dipole said it was limited as L tends to 0. Okay. So here we've got a small L, okay, and we've got some finite charge q. Okay. So we can map that into a dipole. Okay. Effectively what we've got. Okay. Now we know that q is given by I sine omega t divided by omega. That's what q is given by. Okay. So the dipole is going to be that q times L basically, and as L goes to a small number. Okay. So it's going to be, providing that L is small compared to the wavelength. Okay. So it's I naught L sine omega t on omega, which is same as saying P naught sine omega t, where instead of just having P naught to be equal to P, which we had before, or do we have it as P naught? I don't know. It's now I naught L on omega. Okay. Okay. So now we can use all the results that we've developed for a dipole at the origin to a small current element at the origin. Is that clear? Okay. So we're mapping the small current element into being a dipole. Okay. Because the charges are accumulating on either side of that small current element. Okay. So then we can use everything, all the results we've got from before, before, except instead of just P, we have P naught, and that's equal to some relationship between, I naught L and omega. Okay, so then we can get the total energy being radiated from the dipole to be this. Okay, so and you can see that that's just a constant, some constant based on the length and other parameters times an I squared. Okay, and so if we think of if we had a circuit, okay, and it might have some reactances and it might have a real resistance. Okay, and if we have a sinusoidal current going through that circuit, then the energy dissipated by that circuit is going to be I squared times R divided by 2, because it's a sinusoidal and we're looking at the time average. Okay, so we know that the energy dissipated by a sinusoid going through a resistor is going to be I squared divided by R divided by 2, right? Okay, so that would be this, right? So we can equate the two. Okay, so we can get an effective resistance for our small current element as an antenna. Okay, so it's a bit like we start to make a circuit model for it. Okay, so and that's the one that's showing how much energy from the current that's driving that element would be emitted as electromagnetic radiation. Okay, it turns out the actual resistance, we've assumed that this length is small compared to lambda, because we said it's it's going to be it's a small separation, because so it approximates what a dipole is. Okay, it turns out that that for small L on lambda, this is quite a small resistance. Okay, so it's likely that that resistance might be similar to what the ohmic losses are in various components. Okay, so it's probably not a very efficient radiator. Okay, but at least we have a model. The reactive part, there's also a reactive part to that. So if you want a full model of that small length of wire, small current element, then you'd also have to include some model of the reactive component, but that's too complex to handle here. Okay, so we're just going to look at we've just looked at the resistive part, which relates the power dissipation effectively, which is what the radiative power is going to be. Okay, because the only way energy can get out of that system, okay, is via radiation. Okay, except for ohmic losses. Okay, we haven't modeled them. Okay, something different. Okay, so remember we before we defined. Is there any questions on that? No. Remember we also defined magnetic dipoles for. Okay, so and we defined a magnetic dipole as a loop of current. That was our definition. Okay, of that's how we sort of approached it, as a small little current loop. So we could. This won't be in the exam, make it clear from start, but just going over this for completeness, we could also find AR and the magnetic vector potential and the scalar electric potential, and then find E and H for having a magnetic dipole at the origin. Okay, and it turns out we get similar sort of equations here. The actual presentation is a little bit different because we've got this phasor notation. Okay, so this is just a complex sinusoid. Okay, and obviously for the real part of E and H, you take the real part of this. Okay, but you can see again that it involves similar similar terms, and you have irradiated and near field components. Okay, you can see that now E is in the phi component. It is in the phi direction. But before with H, we had H in the phi direction. Okay, and the radiated component of H is now in the theta direction. Okay, so it's the opposite to what we had for the electric dipole. So in some sense, this magnetic dipole results are like the dual of having the electric dipole. Okay, so now the E and H fields just interchange. Okay, but the same amount of power coming out. Okay, so again, you get a far field. And okay, but don't worry about that. We won't have that in the exam. Okay, so it just goes through here. Again, looking at the power radiated. Okay. So that's looking at really small radiators. The actual efficient radiators, you need to have them to be of a length comparable to the wavelength. Okay. So the two typical ones that you see are one where you have the antenna having 2 bits of lambda and 4 to make a half wavelength antenna. Okay, looking something like this. You also see often antennas with just lambda and 4 sticking up from the ground or from the top of your car. Okay, so but they're over a conductive plane. So does anyone know what the conductive plane does? Anyone know anything about antennas? So it acts as a mirror. Okay, so the conductive plane acts to actually form an image of this quarter wavelength conductor above the conductive plane. Okay, so effectively it creates again one of these half wavelength antennas. Okay, so they're the two ones that you see very common. Okay, this won't be in the exam. I'm just going through it to give you a bit of feeling for concepts. okay, and to show how, as well, the work we've done can be used to sort of solve real world problems. Okay. So we've got so far we found for a small the results for a small current element. Okay. So for our extended antenna, which might be have a bits of wire that are lambda on 4 in length. Okay. So aren't small. We could divide that longer piece of wire into small little bits of wire, okay, of dz in length. So we have this long piece of wire going in the z direction, okay, and we're looking at a little section of that of dz in length, okay. Now we could find, since we've got the result for the short current element already, okay. We could find A at some point R, okay, that's due to this dz, and dz's at this position R dash, okay. We could find what that little bit of effect of magnetic potential just from that little piece in the line, okay, and we're looking at trying to find these fields when R is a long way from the antenna, okay. So no matter what Z is, R is going to be a lot bigger, okay. So we're looking at the far field, okay. So that allows us to simplify things. So that allows us to find that this distance between here and the dz we're looking at is approximately R minus Z cos theta, whatever theta is, okay. So we make some approximations when we have this R a lot bigger than what the size of the antenna can be, okay. So and that's what we're interested in. So we're looking at the transmission into the far field, or distances a long way away from it, okay. So again, we can all go and find the E from the dA, and also the scalar electric potential, because we get the scalar electric potential again from A as well, okay. So we can find what E is at the point from that small element, okay. And so we end up with these far field components, okay. So it look a little bit similar to what we had before, but a little bit more complex, okay, because now we've got this distance here, R minus Z cos theta, okay. Again, the fields are at right angles to each other, okay. This is what we expect, okay. And so they go in the propagation directions AR, okay, transverse electromagnetic, okay. So we assume that the current along that conductor is some function of Z, okay. So we assume that we're going to put a sign that the current that's flowing in the lambda and 4 wires on each side, it goes as cos omega t, where omega is 2 pi on the wavelength of radiation we want to emit, or 2 pi times the frequency of the 2 pi times the frequency of the light that we want to emit, or the radiation we want to emit, okay. And we assume that this I of Z is I naught times cos pi Z divided by lambda, okay. That's for the quarter wavelength or the half wavelength emitter, okay. So there's this distribution of I naught, okay. And that may be a little bit intuitive. If we have a quarter wavelength, then we know at the ends here we need we've got nowhere further to push charges, okay, because we get to the end of the line, okay. So if we consider for each little bits of current element, we're pulling and pushing charges along it, okay. And remember in our model that we had charges at either side of that small current element, okay. But if we can see, if we get to the end of the piece of wire, we've got nowhere to put the charges, okay. So it makes sense that I naught would go to 0 at that point. So we don't have to push or pull any charges from the end of the line because we've got nowhere to go, okay. So anyway, that's the assumption that's made, okay. And then to find the total field, okay, we just need to integrate, okay, the E, okay. So at a particular point R and at a particular time, then the actual fields E and H are going to be the integral over Z, okay, of that from Z going to minus lambda and 4 to plus lambda and 4, okay. So you can integrate those functions, okay, and you can do that. As I said, it won't be an exam. You can look in the reader. It's a bit complex, but you can see you get essentially the same results as what we had before, except I think before we just had a spatial factor of just sine theta, but now we get this more complex one, right? Okay, so we get, okay, again, we've got this relationship between E and H, okay, intrinsic wave impedance free space, okay. But so this is the E and H for those spatial fields, okay, and you have this spatial pattern factor, okay, which is different from what we had for a dipole, okay, but not too far different, okay. So if we look at that the magnitude of the fields for the dipole, dipole, and if E is of constant magnitude, then you see it has like a maximum at the equator, okay, because sine theta at pi on 2 is 1, and a minimum at the poles because sine theta 0 is 0, right? Okay, so for the dipole, it has the radiation goes out in this sort of pattern. It's like a bit of a donut, okay. For the lander on 2, which is the 2 quarter wavelengths wire on either side, it also has a similar radiation pattern, okay. So it's a little bit different, but not greatly, okay. So it's again a bit of a donut shape, and you can also have other distributions of so you can have bigger emitters, okay. So we just looked at the half wavelength, but you could have a full wavelength, okay, or more, okay. And they have different spatial pattern factor, okay. So be aware of that. Okay, so we can look at pointing vectors as a transverse magnetic, and we can average the time average radiated power like we did for the dipole, okay. It comes out to be 36 I naught squared, okay. And we can equate that, do that numerically, but we can equate that to a radiation resistance, okay. And it comes out to be 73 ohms, okay. So it's a fairly high resistance, so you should be able to deliver a lot of power to that and radiate efficiently, okay. And that's close to 75 ohm coax cable, and that's why they chose 75 ohms for a coaxial cable, right? Of course, that's efficient to couple to antennas, right? Okay, and some other types of antenna. This is an old antenna that you used to see on TVs. Probably you guys are too young, but when I was a kid, you'd have TVs with these antennas on top of them that looked a bit like that. And they used to have, instead of not coaxial cables, they used to have a bit of this ribbon cable that was a little bit of plastic in the middle, and that was designed for 300 ohms. Anyway, okay, so that's all on radiation or radiation from dipoles and antennas. We're going to move on to the next part, which is quite a big part: wave propagation in linear isotropic media. Okay, so we just have this to do, and then we'll have a small bit on transmission lines. Okay, but this is a fairly major one here. So, is there any questions before we start the next bit? Nope. Okay, so remember in circuit theory we had phasors. Okay, and we said that we could represent currents and voltages by these sinusoids. And remember we were talking about, well, we're just going to look at the steady state behavior of electrical networks. Okay, and we showed that we could solve the differential equations easily having like phasor representation, so that we'd have perhaps V, the actual real voltage is actually the real part of the phasor times e to the j omega t, right? And we do the same thing for the fields in electromagnetics. Okay, it makes things simpler. Okay, so and in electromagnetics, a lot of the actual fields are sinusoids. Okay, of course you think of light or radio waves; they're all sinusoidal oscillations. Okay, of the E and H fields. Okay, so it's quite a good match. Okay, having sinusoids. Okay, so say we've got some vector field x of position x, y, z and time. Okay, so it's a function of space and time. Okay, we're going to represent that with a complex valued vector called phasor. Okay, which is a function of space and it's assigned a frequency omega. Okay, then this the actual true or real vector field x of x, y, z and time is then the real part of the phasor representations times e to j omega t. Okay, is that clear? So it's very similar to what we had for circuit. Okay, so now we can also say, well, that this part of this phasor x, okay, we can say that we can define its position with also a complex exponential. Okay, so where this r is the position, this k is some other